welcome back. Okay, so I just want to finish off some of these things about what intelligent transportation systems are. There are different categories in intelligent transportation systems, starting from traffic management systems. There are some slides about each of these, so I don't want to go too detailed now. So management, this is from a manager's perspective, so you can think of a city. And traveler information systems, that's from a user's perspective. Public transport systems, commercial vehicles operations, advanced vehicle control systems, or AVC. And if you put ATMS plus ATIS to the first two, you get ATMIS, which is another acronym which is common. Both of those are integrated within one system. And you can see, for example, the ATMS is basically where you can monitor things. Tomorrow, when we're going to the ITS lab, we're going to be in a room like this, where when you can monitor what is happening in the city of Toronto in terms of traffic. And yeah.
Like the live.
Yes. Yeah. It's where you see like the live camera footage, and the data comes in there, and they process it. They use it. It's the Toronto ITS Center. That's what it's called. It's in the building. It's in Sanford Fleming. Okay, so ATMS. This is, again, from the management perspective. So people who want the roads to be working efficiently, they want decent speeds, they want high flows. So it's used for traffic surveillance to assess current conditions. So some of the cameras are used to figure out whether there's an accident. That simplifies some of the detection. Optimization of subsystems, so the signals that you have within your system. Access control, so who has access to how ramp metering should be done, whether people should be left to go onto the highway or whether they should wait a bit before accessing the highway in order for us to remain in the uncongested state here. ATMS enabling elements, some of the things that you need for this are the surveillance and control infrastructure. So you need the data that's coming in from loop detectors, from signal heads, and you need the changeable or variable message signs, the VMS or CMS that we mentioned before. Traffic management centers is those type of rooms where all of this data comes in. Of course, they need networking resources and data storage resources, so some of your cloud computing can be useful there. So you have to do centralized control and management decision making. The more data you have, the more global view of the network you have, the better decisions you can make. And the communication links between the actual sensors and the links, because you don't want outdated data. You want to react to changes as soon as you can. A lot of this is fast wireline with fiber. Okay, so ATMS characteristics, you want them to work in real time. So they can have both two different ways of control. One of them is reactive control. So you want to do it currently, and then the other one is proactive control, is anticipate what's going to happen ahead of time. Anticipate that, for example, there was a G20 summit happening, so before that you would make sure the roads are working in a particular way. You would change the traffic lights in order to meet that additional demand. They feature area-wide implementation, so there are parts that are localized, but the information has to be coming to a centralized location. And it's used for highways and for lots of the major streets. And you need here lots of good communication between different municipalities in order for things to work well. That's where the MTO comes in Ontario, because if you go outside of Toronto, if you go, let's say, east or west, if you go north, let's say to York, if you go to Durham or Peel or different areas in the GTA, you need to make sure that across the borders of the cities or the jurisdictions, things are working well and the information is going to one location. Because there's a lot of traffic between these areas. Okay, ATMS examples. adaptive intersection signal control, short-term traffic prediction, adaptive freeway ramp control, freeway incident detection, lots of things that are useful. There's dynamic assignment models, dynamic network optimization models, which is some of the things that we're going to do today. Now, let's see. There are additional things. So there's also integration with geographic information systems, so GIS. Okay, and there's image processing algorithms in order to figure out what's actually happening from the camera footage on the road in terms of detecting incidents. Okay, now ATIS. This is from the perspective of users. I don't know if you have been in the Spadina subway station. They have this for the 510 streetcars, which I think now are not functional. Instead of them, they have buses. But this is one of the streetcars that was used a lot. And they added this system which would show how far the next streetcar is and how many minutes it will arrive. And it would shows you all the streetcars on the map, like live. On the map, you see a point of it moving. Other ones are navigation systems that you see here, and another one is with the computer. So this information is trying to help users choose their navigation options and choose which mode to use. So you were working on what different modes would be useful for your particular routes. I used to live in that area, and I would see, I would look at the screen, I would see if the next streetcar is more than 5 minutes away, I would go out and walk, because it wasn't worth waiting for the streetcar in order to take it. It was useful. Before that, you would wait, and you had no idea whether it was going to come in 2 minutes or 15 minutes. Okay. Other information that is useful is parking information. So we mentioned the street parking example in Montreal, where you know exactly how many street parking spots are available in a particular area before you head there. And so for guidance, there are different paths that you can follow. That's what we're going to be discussing this afternoon. The enabling technologies for these, again, similar to what we had for ATMS. And the additional thing which is useful here is the in-vehicle navigation units. So within your vehicle, if you have a GPS a navigation device, a GPS device, or you're using your a smartphone, for example, that is the additional thing that is required in order to track how you're moving and whether you're supposed to change your route to reach your destination faster. Okay. Next is AVC or AHS. So the point of this is to increase the throughput of the vehicles and to reduce human errors, of course, for improving safety. And there are like different categories of this, including fully automated vehicle controls, where you have a platoon of vehicles, you put them after each other, and you let them run. And what they would do is they would, it's fully automated, so the distances between the vehicles could be very small. And here you can use up the capacity far better. So you have collision avoidance systems also in here. So this is for safety. Now with the newer vehicle-to-vehicle technology that is coming out, what you would have is that if an accident happens in front of you, you would get messages to your car letting you know that there's an accident, and your car would give you a message that you need to stop or you need to slow down. And the important element here is the low delay or low latency. This information should come to you through the vehicles very fast. If it goes through base stations and then comes back to you, it's too late. You've already stuck in that congested area, or even sometimes crashed to other vehicles. And during snow season on the highways here, sometimes you have like 10 vehicles crashing after each other. And this type of technology would help eliminate that. Okay, so I'll skip this. or let me just mention who gets the benefits. You have the individual drivers, you have the road users such as like trucking companies would be able to use this information, and society in general. Transportation systems in general are represent how well the economy is. If the economy is doing well, then the transportation system is busy. That's a good indication of it. But at the same time, if your transportation system is not congested, then that improves the economy and that reduces the wasted time that you have on the streets, which costs money and increases stress, I guess. And you're not producing anything during that time. You're just waiting. Okay. Another element is indirect benefits is creating new service industries and new positions. Okay, there are different obstacles for ITS. And some of them have to do with liability issues. So we were mentioning the autonomous vehicles notion, and there it wouldn't be clear if you had autonomous vehicles who's responsible. If you have an accident, who would be sued, or would the insurance company be willing to pay you back for or fix your car? Additional elements are economic issues. So there's a lot of investment needed for new infrastructure, institutional issues, technical and system integration issues, and societal issues. There's a lot of policy involved in order to take things in terms of technology to the next level. Let's see. So, okay, I'll go through this. Okay. Okay, questions about intelligent transportation systems, like the basics, what you need for them, what are the different technologies, what we might see 10 years from now, 20 years from now. Yeah? Yeah.
How soon do you think we can get automated, like
Automated?
automation starting like vehicles?
Do you want me to say something that would support my work or an honest opinion?
Both?
Where?
I guess North America, just like
North America. Okay.
like consumer-based, mass-produced, like everyone has access to it. What's your honest opinion, and what's like what you want?
Okay. What I would want is 5 years. But what would actually be possible in North America, I would say 20. What would be possible in Europe would be, I guess, 10.
Why?
It's just the way in this field how things work in general, where you have like you compare the technologies, you see what works, you have lots of collaboration. Cities are closer there, so people could interact. You have car manufacturing companies working together with governments, and they're ahead in a few of the things. I know from the specific research, my master's work was on vehicular networking, so vehicular communication between cars, and the technology that I used in my thesis is not ready in North America, but they've already started implementing it in Europe. So it might be ready by the end of next year. There's a policy decision which is going to come out next year. It has to do with the standards of vehicular-to-vehicle communication. Does anyone know what 802.11 is? Okay, in terms of wireless technology, at the physical and Mac layer, the technology that you're using, you might have heard of 802.11a, b, g, and that's the wireless that you're using. There's a separate one called 802.11p, and that's for dedicated short-range communication. That's for vehicles. It has a separate frequency, it has separate standards for it, but it hasn't been enforced yet. At the end of next year, we're going to find out whether it's going to be enforced in North America. Yes?
Is it only vehicles that use
That's a separate frequency for vehicles, and the challenges for that would be the policies and having the SRC-enabled devices in your vehicle. It will cost far cheaper between the devices. You won't have to pay for LTE or 4G and all of those things. There's another question? Okay. Now, introduction to static traffic modeling. So now let's start thinking from a system point of view. So you're managing a city. There are sets of roads, okay? And there are people who want to go from particular sources to particular destinations. So you can think of it as if like you're watching paramedics and you want things to work well, not putting green lights on all the traffic lights and trying to make the cars crash. So what would be a good transportation system? What performance measures would you look at to say this is working well? Flow. So flow where? On what link? Everywhere, right? You're trying to make sure that the capacity that you have on different links across your transportation network are being used. So you're close to the maximum flow that you can achieve in most of the places, and you're trying to avoid congestion. You're trying to stay in the uncongested state. Okay, so what if you have knowledge of where everyone wants to go? Right? What would you do? Yeah?
More roads or wider roads to that destination?
Yes. On the long term, you can create more roads to that destination. That's a planning issue. Okay. So you're planning in a way so that people avoid some people are not taking other people's way. So it's an optimal assignment. You give every single person a route of what to follow, right? Which way to go. So now we're going to be looking at this. We're going to be looking at how this is actually done by engineers, how, for example, engineers use, in the industry, use softwares like Paramex in order to do this, and what would be beneficial for whom, for users. This is similar to what we had in the morning, right? So at the beginning, when you didn't know any routes, you went through one route, and you were stuck in traffic. Because there were slower people than other people, plus the density was high. But if you know more, if you know multiple routes, then you can distribute the vehicles onto different routes, and then things would be better. Okay, so what we need for this is the traffic flow model, how the traffic is flowing. So we mentioned some of that before with that macroscopic model, where you make the time limit small, and you calculate how many vehicles are going from section to section in the road segment. Then you have the network or routing model and how they would go through your system. So what would be a route? If you think of if you have a network, okay, what would be a route made of? You're going from like point A to point E, right? Do you go that, like, if you're flying, you can go that way directly. If you're driving, most likely what are you going to do? You're going to be taking different links along the way, right? Okay. So this is where what Marwan said is interesting. When you're taking links on the way, other people might be taking those links in order to go to a different route, right? And you need to make sure that those links, those critical links, for example, are not used a lot, and your assignment is done in a way where people are not getting in each other's way. So network modeling, first of all, you model the nodes and the links. In transportation networks, what would those be? What would be a link? A road or a road segment. What would be a node? Excuse me? Other than lights. Lights is one of them. Intersection between road segments, right? So link and intersection, and then you do the traffic assignment modeling. Okay, so this is a physical network. Okay, this could represent a transportation network. So this would be an intersection between roads, and the lines would be the actual roads. And of course, you can have parameters of how many lanes each of these have, how much time it takes, what's the speed limit on each of them. If you have ramps, you would have a smaller speed limit on the ramps, all of those things, as you can see them on Paramix. Okay? So now you're going to learn how actual traffic engineers program these things, and so that tomorrow when you're using Paramix, you'll understand where these are coming from. But you're basically using whatever has been worked on quite a bit, and then you're changing stuff in it. Yeah. So traffic assignment, let's go through this. Okay. So there are a couple of things that we need to consider. First of all, so the first one, the lower the travel cost, you have a higher demand, right? And how do we define the lower any cost is, the higher the demand for that would be. Think of now a particular highway. What is the travel cost that you have on it? If you're for the user, yes. Time, right? Fuel consumption. The more time you spend there, you're wasting time, and you're wasting fuel. So, or battery, if it's an electric vehicle. So usually people have a higher demand when the cost is lower. Okay, in terms of supply, actually let me jump to this one. This is the free flow time. So this is the travel cost. When you increase the volume of a link, what happens? So this is the cost. Okay, this is the time that you're spending. Travel cost could be travel time. You can just think of it that way. This is the volume. This is the number of vehicles on the road. What happens when you increase the number of vehicles on the road? Increase the cost. Why? There's more congestion, and you can't go at the speed that you want it to go. You have to go slower. It's going to take you more time. Okay? So this is the referred to as a link performance function. It just shows you how much time it's going to take you if more people are using the same road section. Now, why is it then that we might have, let's say, ramp meters that would prevent vehicles to enter the highway, and we make them wait a bit so that the highway flows well? Why do we do that based on this curve? Yeah. By waiting a short amount of time at the ramp before coming out to the highway, we're limiting increasing the volume here. So we will be staying towards the left, and when they actually go onto the highway, things are far better for them. However, if we let everyone onto the highway, which is currently the case, in Toronto at least, then you have huge congestion because everyone is going to suffer with a long travel time. Okay. Now, this is something interesting. You put the demand and the supply together. So you put the both curves together, and you get a match here, and that's the equilibrium. Okay? That's what ends up happening when you put a demand and supply curve together, and this is common in various fields. So you come in and say, there's congestion. I'm going to make things better. I'm going to build a highway. Or I'm going to add a lane. Right? So new freeway, low cost. What happens? What's the first thing that happens? People find out about it. So everyone knows and wants to use it. Okay, so you have your new freeway. Everyone wants to use it at the beginning. So more people start using it. Then what happens is it gets congested. After it gets congested, then your cost starts going high. What does that do with your demand? Your demand decreases, right? So people stop wanting to go onto that highway. They start using other routes. So it's less appealing. Some people give up. So you move here. So the demand decreases. And then things get better because less people are using it. And then it moves here. and then you move along, you turn around this as a spiral, and then you end up at an equilibrium state. Okay? An equilibrium is attained somewhere here. This is when the highway is new. Okay? Now, you come to this and say, I'm going to build an additional lane here. I'm going to add an additional lane. What is going to happen to the curve? Shifts. Which curve will shift? First. Yes. The performance curve will shift first, right? The performance curve will shift right. Okay? Will shift right, and the intersection would be at a lower point. Why would it shift right? Because my cost for the same, or my travel time for the same volume is going to be lower. So the green one would shift to the right. It would just move right. Then what would happen? What would happen? How do people react to that? So at the beginning, right after I added my capacity, okay, right after I added my capacity, things improve, right? Because I have more capacity, my travel time is less. Next, people start hearing about it, right? People start hearing, okay, this is doing better. Then what do they do? What changes on the curve? The demand. So the whole demand curve then shifts. The demand curve so the performance has shifted to the right, then the demand curve shifts to the left, and what you end up having is you don't have that big difference, you end up getting a smaller difference. Okay, why? Because you also shifted the demand. And that is after people got to know about this faster highway. Do you have questions about that? I want to make sure that it is clear. Yes? Yeah, because people know that the cost is lower, you increase the demand that you have for the road, that's why it shifts. Okay, the performance, this function would move to the right because for the same volume would have a lower cost. And then for the demand, for the same volume would have, it would shift to the right. Because for the same volume, you'd have a higher demand. It should shift to the right, not to the left. Okay, so both of them would shift to the right. Mm-hmm. And I'm not saying you're not going to end up benefiting. You are going to end up benefiting, but the most benefit you're going to get is the first few days when no one knows about it. Okay? So when you make the change, this shifts, no one knows about it, the demand is as is, your travel time is here rather than being here. Okay? So if the green curve is here, then your travel time is here. You have gained, let's say, 15 minutes in your ride. But then what happens is when the demand curve also shifts, okay, the intersection point moves a bit upward, then you lose a bit of the gain that you had. Yes? What do you mean, go up?
Yeah, because if the performance is increasing, then will the demand...
The demand, do not confuse these separately. The demand is dependent on the volume. It's not dependent on the performance function. You have them here. Okay? The lower the cost, the higher the demand. The higher the volume of people, the demand will decrease. Right? And then you put them on top of each other and find the intersection to find the equilibrium point of what ends up happening. Okay. So, there are two ways of assigning traffic on a road. One of them is called user equilibrium, and that is what rational people would do. Where did you hear that term? Yesterday. In what? Game theory. So if people act in a rational way that would improve their own performance, basically, that's what we call user equilibrium. So you have multiple routes between any OD pair. OD stands for origin destination. And tomorrow you'll get to edit and change the OD pair. to if you want to create a congested state, just add traffic in the OD pair. I've done it. It's fun. So actually, in one of the activities, you have to do it. So in here, we're assuming that motorists are rational, that the demand is constant during a particular time, which is what we're seeing in panoramics. But actually, what happens is during the day, demand varies, and it varies with cost. So we saw how the demand curve shifts based on what is happening, right? And we're also assuming that supply is constant. We're assuming that there are no accidents happening, and based on that, we're modeling. But again, if accidents happen, things are not going to go the way we had expected. And the other thing is we're assuming that users have perfect knowledge of what's happening, of what the travel times of the various roads are, okay? Which is not like fully valid to this date. In order to have any type of assignment, you have to have these assumptions. Okay. So I'm going to explain these to you, and then you're gonna solve them. You're gonna come up with the travel times for these different strategies. Okay. Okay. First of all, user equilibrium. Now, you have a source at the beginning, and you're trying to go there. This network is called the fish network. It has these two links. Either you can go through the upper route or through the lower route. What this principle says, the equilibrium state that you end up having, is users will be on a particular route. If they know that the other route is better, they change their route to go to the other one. What ends up happening at the end is both of the costs on these routes are going to be identical. Okay? Remember yesterday in game theory we were saying that you arrive to a point where the equilibrium state is the Nash equilibrium. You don't have any benefit of changing your strategy, of changing your route here. Okay? That's what ends up happening. So, for example, you have these two different volume delay functions. So this is the performance functions that you have. Based on the volume, you have the travel time. What ends up happening, even if they do not actually look similar, you'll end up at a point where the travel times are going to be identical. So a user would not have any incentive of changing their route, because if they change their route, they're going to suffer. Remaining where they are at equilibrium would be the best thing. But this means that everyone will end up having the same travel time, right? Whether they take the first route or whether they take the second route. But that doesn't mean that we have the same number of users on each of these, because one of them could be longer and one of them could be shorter. Okay? So the activity in the morning, if I made you repeat that several times, the second one, so going through two different routes, what would end up happening is none of you want to take more time, right? So the route which is taking more time, people would shift from it to the other one. Like you'd come back and just ask your friend, they're like, oh, I was here in 2 minutes and 2 seconds. So you change to the other one, and after a few iterations, you settle on both routes having the same travel time. Okay, so the principle in user equilibrium is no one can improve their route by switching their routes. Okay, now let's move to the other one. Any questions here? Well, the thing is, today you don't have absolute knowledge of if you change what's going to happen on your other road. But here the assumption is users have perfect knowledge of routes and costs. So users know that if I shift to the other one, it would cost me this much, it would take this much time. So that's the assumption that we have. If I go through that upper route, which is usually longer, or if I go through the lower one, which is usually shorter, with user equilibrium, what's the difference in their travel times?
The lower is like faster.
No, they're not. What ends up happening in user equilibrium is people shift from one route to the other one, that even though usually a route takes longer, less people are going to be using that, and more people are going to be using the faster route, but what you're going to end up with is both routes are going to take the same exact time. Okay, that's the principle, that the travel time using the upper one and the travel time using the lower one is going to be the same. And this is also common when you have multiple, like 5, 10, 20 routes. That's what ends up happening. Now let's jump to system optimal. User equilibrium is what happens today in reality, because you can't, we don't have the mechanism yet to tell people, take this route, you take this route, you take this route. So that's what ends up happening. The measurements from the real measurements from like the road sensors, when we compare them to the results, it's very similar to user equilibrium. If we look at system optimal is what municipalities, cities, transportation people want to see. This is the best usage of the roadway system. Okay? This minimizes the travel time for all the users together. So what this means is here I have two different curves for the two different links, so the upper and the lower one. What I want to do is the derivative of this. So I don't know if, whether you know this. The derivative of a curve is what would be the tangent slope there. So this is the marginal cost. If this is the actual cost, the derivative would be measuring the marginal cost. Marginal cost defines the cost of one additional user. Okay? So if I add one additional user on that link, what would be the cost or the travel time of that user? Okay? So this, what this does is it makes the marginal cost of the two links equivalent. Okay? Instead of making the actual travel times equivalent, it makes the marginal cost equivalent. That ends up minimizing the total travel time for all the users, and the travel time is based on the number of vehicles on this route times the travel time plus the number of vehicles on this link times the travel time on that link. Okay? If you take this thing and you minimize it, so basically that's through a derivative. You have a parabola type of thing and you're trying to find the minimum. What you end up getting is the marginal costs have to be equal. Okay, here's the formula for it. So you end up getting that the marginal cost has to be equal. Let's see. Okay, so here it is. So the link travel time is equivalent to the actual number of vehicles that are using it. So Q, which is the flow, and the travel time on that Q. So how can I find the actual number of, if I have, let's say, 100 vehicles on link 1, how do I find the travel time on the curve? Tell me what I should do with my finger. I want to make sure you understand this curve. If I have 100 vehicles, what is vehicles? Where do I find it on? Which axis do I find it on? X-axis. Okay, so I start from here, I go to 100. And then what do? I go up to link 1. The point that I got, this, what is it? The travel cost of one vehicle. Okay? So what is the travel time for the vehicles on that road? It's equivalent to the number of vehicles, so the 100 times the travel time that I got there. Okay? And I do the same thing for the other link. In here, what's going to end up happening is instead of having an intersection that I had here, what's going to end up happening is I'm going to go to the points where the marginal costs are equal. Okay? So as long as this is the cost of adding an additional vehicle, moving it from here to here is better. And how do I get that? By the marginal cost. Then I take one vehicle from here and I move it here. So I go down here and I go up here. So let's take this example. I have 200 vehicles that have to go through my system. So I have 200 vehicles there. They need to go to the other side. Some of them have to go through the upper route. Some of them have to go to the lower route. How many do I send from the upper route and how many do I send from the lower route? It depends on their actual curves. So they're not the same distances. They have different travel time equations. That's why they look very different here, right? So what do I start with? Let's say we start with half-half, right? So I start with 100-100. I come here. Is this the best? Okay. It's not the best because, why? I take the slopes there. If the slopes are different, then what can I do? Again, let's go back to what the slope measures. The slope of each of these curves tells me if I add one additional vehicle on that road, how much time is it going to take? Okay? So I am here on this curve and I'm here on this curve, right? I'm at 100, so it means the total is 200. I'm meeting that. Now I want to see if I could change things to make them better. I look at the marginal cost and I look at the marginal cost. The marginal cost here, this is higher than this one, right? So in here, let's say it's, I don't know, I'm making stuff up. This is 40 and this is 30. So what does that mean? So every vehicle, every additional vehicle on link 1 would take me 40 minutes, while every additional vehicle on link 2 would take me 30 minutes. So what should I do? Reroute vehicles, right? I am here now. What I can do is I can decrease the number of vehicles on link 1 and increase the number of vehicles on link 2. I need to make sure that the total is 200 because the 200 have to go across, right? So when I decrease this, I get, let's say, 35, and then I have 38 here. And then all of a sudden, my marginal cost on the other link is higher. Then I shift back until I end up with the slopes being identical. What that would mean is any additional vehicle that I add on link 1 or link 2 will have the same exact additional travel time, right? Which would mean I can't reduce my total travel time anymore, and that is where I stop in the system optimal. Okay, questions, please. What is the marginal cost measuring here? The slope of the travel cost. What's the meaning of it? How can I explain it? If I get the slope here and I'm getting 40, what does that mean?
So the volume is your amount of your cars.
Volume is my amount of cars, yes.
And the Y is cost. So if I, for example,
I'm here.
yeah,
I go up, I have that travel cost. That's my travel cost. What does the slope at that point mean? I come there. The slope is the tangent here, okay? What does that measure? What is the meaning of that?
the money that you pay.
The money that I would pay for any additional vehicle I add to it, okay? On this, if I add any additional vehicles, I move this way, okay? At each point there, the derivative, or the derivative of the function or the slope at that point would measure how much it would cost the whole system if I add one more vehicle, how much travel time it would take, okay? Yeah, depends on what demand you have. This is going to keep on going up. It's not going to become fully straight. It's going to keep on going up. Okay, so now that we know that the slope measures the cost of adding an additional vehicle, why do I need to make the marginal costs equal on two different links? The total cost for each of the routes is not going to be the same. Okay, on this curve, the total cost is only the same no, let me explain it from here. This is user equilibrium. This is on a point here, when you have an intersection, the number of, the travel time per vehicle on that link is going to be the same. So if you go to link 1 or if you go through link 2, it's going to take you the same time. In here, that's not our goal. what system optimal says is, in order for me to have the best system for everyone, a few people have to take a longer route, okay? And more people can take the shorter route. But overall, if we repeat this several times, everyone will end up having the lowest total time on average, okay? But when I'm running on route, I'm sending some people on route 1 and I'm sending some people on route 2, people on route 1, which is longer, are not going to arrive home like the same instance while people from route 2 go. Okay, so it is going to take 5 minutes or 6 minutes longer. But the next time I'm giving routes, I will give these routes for the other users, and I will switch them around so that it's fair. Like I'm providing a fair assignment to everyone. What would happen if people start acting selfishly is I end up getting user equilibrium again. If people say, okay, I don't want to arrive 5 minutes late, I want to go to the other route, you get to user equilibrium. What ends up happening is everyone suffers together.
So it's like game theorem.
Yes, so user equilibrium assumes rational behavior, where you have basically selfish behavior, and whatever, like you don't care what someone else does. But with system optimal, this is what is actually the best. And now you're going to solve examples to see the results of each of those. And then you're going to solve another one where you will see where user equilibrium is really, really bad for everyone. Okay? So any questions about system optimal and how we're trying to, how we achieve the result with system optimal? Okay, what is system optimal good for? Who wants system optimal? Planners, transit planners, cities, and basically, on the long run, everyone wants it, right? What are obstacles in trying to achieve this?
You can't actually tell people go 50 here, go 75 here.
You can't actually tell people where to go, but before that, you don't know where people want to go, right? No one now has knowledge coming from everyone using the road that they're going to be going to a different, to this particular destination, because there are some privacy issues with that. And the technology isn't there. Not everyone has the devices through which they could communicate to get that type of information. Okay, so solving for user equilibrium and system optimal. So for user equilibrium, please write these down. What you need to do is you equate the route time. So you equate travel time from different links together. And for solving system optimal, you equate the marginal cost. So marginal cost of 1 equal marginal cost of 2, and so on and so forth. And there are different, so this is an iterative procedure. This is what you might start with, and then you shift until you reach a solution. And there are different like software tools that would do this. Paramix, by the way, gives you something similar to user equilibrium. If you run it around like 9, 10 times and you average them, you get very close to user equilibrium. Because the way the vehicles move in it now is basically with rational behavior, trying to minimize their costs. Okay, so user equilibrium, you're going to equate the travel times. System optimal, you're going to equate the marginal cost or marginal travel times. The only two things that you need is for user equilibrium, you have to equate travel times. So travel time of link 1, it should be equal to travel time of link 2. For system optimal, the marginal cost of link 1 should be equal to the marginal cost of link 2. I'm going to give you around 15, 20 minutes. You're doing this individually. I want to make sure everyone gets this. If you have questions, please ask me, raise your hand, I'll come and help you. So let me explain the problem. An eastbound urban corridor is composed of a freeway splitting into two freeways. So you have 2,500 vehicles per hour coming from the main highway, and then you have 1,000 vehicles per hour coming from an on-ramp. They're running in parallel as shown. The performance function of the first freeway is given by T1 is equal to 4 plus 3 Q1 over C1, where C1 is the freeway capacity of 2,500 vehicles per hour. T1 is the travel cost in minutes, and Q1 is the volume using the freeway in vehicles per hour. So that's the upper link, where you see Q1. The second freeway, which is the lower one, has a performance given by T2 is equal to 6 plus 2 times Q2 over C2, where C2 is the capacity in vehicles per hour. The flow on the second freeway can be described by a Green-Shield relationship of the form U is equal to 100 minus 0.625 K. So this is the formula that you had written before. K is the density and 0.625. Instead of it, you had a different ratio. Check your notes. If you don't have it, I can help you and tell you what it is. Where U is the speed in kilometers per hour and K is the density in vehicles per kilometer. If the total demand from the main line upstream of the bifurcation is 2,500 vehicles per hour and the total on-ramp is 1,000 vehicles per hour, what would be the volumes and travel times on both freeways downstream of the bifurcation under user equilibrium? So for now, you're doing the first part. The second part has to do with system optimum. So you have 15 minutes, let's say, in order to come up with the user equilibrium outcome. How many vehicles would be using the upper link? How many vehicles would be using the lower link? The travel times are given by T1 and T2. You need to make sure that the vehicles that you have on the left all go across. Okay? All of them are going right. And use the formulas that you had before. If you have any questions, you can ask me. Please try to do this individually. Do not help each other. Unless you do this yourselves, you won't actually understand it. Any questions before you start? I'm going to leave this on so you have the data there.